Hello, I am Birhanu. I'm going to present our paper, Best Effort Adversarial Approximation of Black Box Malware Classifiers. This is joint work with my former graduate student, Abdullah, who worked on this with me for his master's thesis. In this talk, we consider what has become a common setup in machine learning as a service. So given a black box access to a machine learning model, clients or users are allowed to repeatedly query this model through a prediction API and observe the outputs of the model. However, if the client is malicious, it can use the input-output interaction to essentially steal the model. This attack is known as model extraction or model approximation, and it's the focus of this talk. We will be using a naturally adversarial domain, malware classification, as a case study, but the ideas we discuss here are fairly generalizable to other classifiers in other domains. So what are the motivations for model extraction? And the first one is essentially stealing intellectual property. So training machine learning models is a pretty expensive business because there's a great deal of compute, data, manpower that goes into producing machine learning models that work well in practice. Secondly, machine learning models are increasingly trained on privacy-sensitive datasets, which motivate adversaries to probe models to leak personally identifiable information. A natural example would be a model trained on patient data. Another adversarial motivation is to increase attack effectiveness when access to the model is purely black box. The adversaries try to approximate that model and then attack the approximated model in a white box setting so that they get direct access to the model parameters or the details of the model to perform attacks such as adversarial example generation. Our question in this talk is, given black box access to a model, such as a malware classifier, can we extract a similar model that solves a similar task reasonably well? The first possibility is whether exact solution or exact extraction is achievable. Like the typical machine learning problem, unfortunately, this turns out to be unrealistic because there is potentially multiple models that compute the same function but have different representations. As a result, the best we can hope to achieve instead is some functionally equivalent model. So our question is reframed as follows. Instead of aiming for exact extraction, we aim for a functionally equivalent model that we can approximate with some confidence. So this confidence is essentially described using a distance metric. So a black box model and its extracted approximation fulfill the criteria of some distance metric, where distance is, for example, measured by the percentage of predictions on which the two models disagree. So the smaller the upper bound epsilon here, the closer the decision functions of this models are. So functionally equivalent model extraction is achievable, and we know that because previous work has demonstrated this, but extraction success really depends on assumptions made about what the adversary knows and what the adversary can do. So essentially, adversarial knowledge and adversarial capabilities with respect to, for example, the knowledge and the capability of the adversary with respect to the model architecture, the parameters, the features, data set, and also the output fidelity as well. So in this regard, there is a range of assumptions made by prior work regarding the prediction output fidelity, the model architecture similarity, the feature similarity, and the assumptions on cross-model transferability when they do model extraction. In terms of strategy, prior techniques have used techniques ranging from equation solving, optimization, generative adversarial networks to reinforcement learning. So our setting our model extraction setting is as follows. So we consider the most challenging threat model for the adversary in the face of very limited access to input examples, typically like 10%, the maximum of the size of the training set for the black box. In terms of output label fidelity, we assume that the adversary has access only to the label given an input. And for feature representations, we assume that the black box model and the extracted model have different feature representations. And finally, for the training sets, we assume disjoint training sets. So given this strictly black box and seemingly difficult threat model, the question we ask is, how close can the extracted model get to the black box model under the most challenging threat model we just described? So that background on the threat model and the problem setting, let me now highlight some aspects of our work, our approach essentially. So our model extraction approach starts as follows. So we're assuming a black box model is there and deployed, and we have API access to it. So the adversary uses an approximation dataset to query the black box model and obtain the labels. Then the adversary performs what we call feature representation mapping, or in our case, it's particularly mapping the byte representation of samples, Windows executables in our case, to a pixel representation of this Windows executable samples. Then using these mapped representations of the approximation set, the adversary then trains the last layer of a pre-trained image classification model to obtain the extracted model. Finally, the adversary uses a separate test set to compare similarity between the black box and the extracted model. So to zoom a little bit more on the strategy we use here in the approximation set labeling stage of our approach, we note that the training set for the black box, and when we compare the training set for the black box and the approximation set, so X prime is the approximation set, X is the training set for the black box, X prime is much less than X, and these two data sets are disjoint. So the representation mapping, the key idea of the representation mapping is that given the byte sequence representation of Windows executable samples, we want to obtain the equivalent pixel representations. So the key benefits here are, first, we don't need to do manually feature engineer. So once we move the representation from byte sequences to pixel representations, we can take advantage of representation learning techniques such as deep learning to train our models. Secondly, since there is a huge advancement in the image recognition domain or image classification domain, we have already pre-trained models from which we can transfer the knowledge that they have distilled through repeated training on huge data sets of images. Here is the key intuition for our representation mapping. So the idea is values close to each other in the byte space of the samples are also placed close to each other in the pixel space. So the mapping methods that we used are the entropy-based mapping and the color-Hilbert-based mapping. So in entropy-based mapping, what we see is the byte values are mapped into a Shannon entropy value between 0 and 255. And in color-Hilbert, the byte values are mapped to a pixel intensity values. So in this work, what we assume is that this representation mappings will preserve the structural integrity of the original samples in byte sequence and migrate those representations into pixel representation, the corresponding pixel representations. So here is an example for real representation mapping. So on the left, you see a representation mapping for a benign Windows executable, and on the right is a representation mapping for a malicious or malware Windows executable for both entropy and color Hilbert. So as I said earlier, entropy is more focused on identifying regions that stand out, while color Hilbert is focused on individual pixel values. And from the images here, that aspect of the two techniques is quite evident. So on leveraging transferability for extraction, once we have the mapped representations from bytes to images, then we use Google's Inception V3 model, pre-trained model, and train only the last layer, or the softmax layer in particular, on our samples, on the samples that we mapped from bytes to images, and then we obtain the approximated or the extracted model. Okay, so that kind of gives you a highlight of what the approach is, but the details of the approach are obviously in the paper. So next, let's see what data sets we've used, and then we'll discuss the results we've got from our evaluation. So we use in this work, we use two data sets. The first one is what we call the Custom-MalConv dataset, where we collect all the samples manually and train a convolutional neural network black box model based on MalConv architecture, which was introduced a few years ago. Since we have to manipulate the samples for representation mapping, we need to have a we need to have a data set that we can control, and that is basically the motivation of having our own data set. Secondly, we use the EMBER dataset to evaluate a slightly relaxed version of our threat model, which I will describe later, where the adversary essentially knows the features of the black box model. Okay, so now let's move on to the results of the Custom-MalConv dataset, and then I will later describe the results of the EMBER dataset. Okay, so in this plot, what we see is a comparison between the two Inception V3 based approximate models, which were trained on image representations of the samples. These are the blue and the green lines. And the black line indicates the progressive extraction of a MalConv model that was trained on a byte sequence. So basically, we're using the black line as a baseline to compare it against the two models that we extracted using our core technique. So the relatively better accuracy of the two Inception V3 models suggests two things. First, the pre-trained model really boosted the extraction accuracy. So that's quite evident from the two lines, the green and the blue. And secondly, even if we perform model extraction on the same feature representation, notice the black line, that may not necessarily result in high accuracy model extraction. So this was a particularly intriguing observation from our experiments. Next, we compare the similarity between the models on a separate test set that is disjoint with the approximation set and also the training set for the black box. So here what we notice is that the entropy representation achieves the highest agreement between the black box and the extracted model, while the same feature representation, namely the byte sequence-based MalConv model, gives the lowest agreement between the two models. Okay, so next we'll look at a slightly relaxed threat model where everything is the same except that the adversary knows the features, for example, from public knowledge. So moving on to the results on EMBER dataset. So the equivalent plot for progressive model extraction in EMBER dataset is this one. So here we have 4 models that we extracted: decision tree, random forest, k-nearest neighbors, and light GBM. By the way, light GBM is also the model that was shipped with the EMBER dataset. So we used that as the black box, and the light GBM extracted model here is used as a baseline to compare it against, the other 3, the decision tree, random forest, and KNN. Okay, so looking at the decision tree, random forest, and the light GBM model, compared with the Inception v3-based model extraction, they have lower validation accuracy, roughly in the range 85 to 88%. On the other hand, looking at the blue line, which is KNN, it shows that about more than, I think, 90% validation accuracy is achievable from this plot, which is comparable with the Inception v3-based extraction. So the key takeaway here is that even if we relax the threat model, what we obtain, the accuracy of the extracted model that we obtain, is not much different from what we obtain in the strictly black box or the more difficult setting for the adversary. So that speaks to the strengths and the validity of the black box approach that we use in this work. Okay, and lastly, comparing the similarity of the various models we extracted using the EMBER dataset, we notice the KNN stands out as the most accurate and the closest to the black box model. Still, the main takeaway here is that our strictly black box and highly constrained extraction strategy is as accurate as a relaxed threat model where the adversary knows the features of the approximated model. So I hope I gave you a highlight of the results, and if you're interested to explore more about this problem in the setting that we described it, there are more details of the approach and the experiments in the paper. Okay, so wrapping up, so in conclusion, we showed in this work the feasibility of adversarial approximation of a black box machine learning model in a strictly black box setting. Our results shed light on the fact that different feature representations may not necessarily hinder close enough approximation, and disjoint datasets still result in successful approximation. More importantly, a pre-trained multi-class image classifier, such as Inception v3, can be repurposed to approximate a binary malware classifier, which interestingly demonstrates the scope of transferability beyond cross-model, and we show it in a cross-domain setting, which means we took a model trained for the image classification domain, we repurposed it for a malware detection domain, and we extracted a black box model by leveraging the knowledge that we obtained from that pre-trained model in the image classification domain. So that's essentially the main takeaway of this work. So with that, thanks for your attention, and I look forward to your questions.